Hi everyone. In the previous video, we defined the inverse hyperbolic functions, and in this video, we'll look at their derivatives and antiderivatives. So let's state the derivatives of arcsinch, arccos, and arctange. First of all, the derivative of arcsinch is 1 over the square root of 1 plus x squared. Notice this is really similar to the derivative of arcsine, but this one has a sum of squares rather than a difference of squares. So we can use this to get an integral formula which is similar to the one we know for arcsine, but this time we have a squared plus u squared rather than a squared minus u squared. And the formula in this case would be arcsinch of u over a. The proof of all this is nearly identical to what I showed you in another video with arcsine, so I won't bother showing all the details here. Next up is the derivative of arc cos, which is 1 over root x squared minus 1, which leads us to another integral formula, which is again similar but slightly different than the one that we know for arcsine. This time we have u squared minus a squared rather than a squared minus u squared. And we just found that arc cos is the function that has a derivative of that form. Last up, the derivative of arctange is 1 over 1 minus x squared, and that leads us to an integral formula which is similar to arctan, but allows us to have a difference of squares instead of a sum of squares in the denominator. As you might expect, this integral evaluates to 1 over a arctange of u over a. I won't bother proving any of these since again I would basically just be repeating the same arguments I gave you before with inverse trig functions, but I do encourage you to convince yourself of all of this by trying to prove these for yourself. And you can always refer back to the videos on inverse trig functions for a reminder of how those arguments went. In any case, make sure to write all these down on your formula sheet for future reference. Let's try an example. When it comes to calculating this integral, the first observation I would make is that it's not of the form f prime over f, and there's no other obvious substitution that could get the job done here. So having said that, we know that we should also look for sums or differences of squares. And we can get one of those by completing the square. Let's try it. Pause and check for yourself that completing the square gives you the result that you see now. And note that we have a difference of squares in the denominator. That would have been a problem for us if all we knew about was arctan, since that formula requires a sum of squares. But now that we also know about arctange, we don't have to worry anymore about whether we get a difference or a sum because we have a formula to deal with it either way. In this case, since we have a difference of squares, we should be thinking about the arctange formula that we just came up with. So to match the formula that we're trying to use, we might start by writing our integral as 1 over u squared minus 1. But if we do that, there's an implication that we just let u equal x minus 1. So don't forget that we need to perform this substitution properly and keep track of the impact that this has on du. In this case, du would be the same thing as dx, so the substitution works out pretty nicely. Now, our denominator currently reads as u squared minus 1, but it would be better if it were 1 minus u squared, since that would more clearly match the form of the formula that we're trying to use. But that's no problem because we can make this happen by just factoring a negative out of our denominator. After doing that, this now clearly matches our formula, where in this case a is equal to 1. So we can go ahead and evaluate this to arctange of u. As a final step, just don't forget to express your final answer back in terms of x and you're done. Another method you could have used on this example is partial fractions, but in my opinion, completing the square and using arctange is a lot easier. So this serves as another reminder that partial fractions should really only be used as a last resort. Let's try another example. Here we have another situation where we have a quadratic function under a square root. So if we complete the square, we can get a sum or difference of squares. And we don't have to worry about which one of those we get, because whether it turns out as a sum or a difference, we've got a formula to handle it either way. It's going to be inverse trig or it's going to be inverse hyperbolic, depending on whether we get a sum or a difference. So pause here and try to work this one out for yourself, and when you're ready to see the solution, let's continue. Completing the square should have provided you with this result as a first step, and after that, there's actually more than one way you could proceed. In my opinion, the easiest way is to let u equal x plus a half. In that case, du would be exactly the same thing as dx, so our integral can become what you see now. And the expression under the square root is shaping up to look like u squared plus a squared, which suggests using the Arctange formula. But actually what we have here is 2u squared plus a squared. So something needs to be done about the 2 in front of the u. My suggestion is to factor it out. Just be mindful that if we do that, it needs to be factored out from all the terms in the denominator. So factoring it out from both terms gives us u squared plus 1/4 now. And the 2 that we factored out can be brought all the way in front of our integral, but it does still need to remain under a square root. Now remember, all of this was just an excuse to get the expression under the square root into the form of u squared plus a squared. But what's the value of a in this case? Well, a must be a value whose square is 1/4. If we express 1/4 as a half squared, we can now more easily see that 1/2 is the value of a in this case. Now that we've done this, we can go ahead and apply our Arctange formula, and notice that dividing by 1/2 is the same thing as multiplying by 2, which is why I got Arctange of u times 2 in this case. As a final step, express this in terms of x and you're done. As I suggested a few times, the main takeaway from this video is that we no longer need to worry about what result we get when we complete the square. Whether it's a sum of squares or a difference of squares, we have the formula for getting the job done either way, and that's really the most important reason why we study hyperbolic functions in this course. That's all for now, so I'll wrap things up here and see you next time.